So using the example of the die again, where we have 6 possible values, we have a 6-dimensional vector space, 6 basis vectors, each one corresponding to a different possible measurement. We have the unknown state, where each value on the die is equally likely. That's when it's tumbling through the air and it hasn't landed face up yet. We're now going to consider a situation where someone else throws the die, but they hide it. All they do is they tell you that it's an even number. So for us, that means it has to be in one of the even states. It has to be in either 2 or 4 or 6, and we have to normalize that, so we put a 1 over root 3 in front. In component form, that's just 1 over root 3, 01, 01, 01. We can calculate the probabilities of each possible value of the die when it's in the even state, and we simply apply our normal rule, taking the dot product with the even state, squaring the result, and you'll find that for odd numbers the value is 0, and for even numbers the value is 1/3, which is exactly what you would expect. If it's in the even state, there has to be 1/3 of a chance of getting each of the possible values. So for example, the probability of it being a 6 when it's in the even state, we simply take the dot product of 6 with the even state, which evaluates to this, which is 1/3. Now what about the probability of it being in the even state in the first place? In purely classical terms, these are mutually exclusive possibilities. So the probability of one of these states is the sum of the probabilities of each one. So it's the probability of throwing a 2 plus the probability of throwing a 4 plus the probability of throwing a 6. And each one of those is a sixth, which is 3/6, which is a half, which is exactly what we would expect. Half of the values are even, so we would expect there to be a 50-50 chance of throwing an even or an odd state. In terms of our vector model, the probability of throwing even, given that it's initially unknown, we simply take the dot product of the even vector with the unknown vector and square the result, and the root 3's and root 6 come out. This, the row into column, gives a 3, which is root 3 over root 6 squared, which is a half. So it's exactly the same value as we would get through classical reasoning. I'm now going to define a very similar state to E, but we're calling this E prime. And just like E, it is a sum of the 2 state and the 4 state, but instead of plus 6, this time we're doing minus 6. So in component form, that would be have a minus 1 in the final coordinate instead of a plus 1. Now, this isn't all that unusual. We've defined states like this before. If you recall, when we had the dice with coloured stickers on it, the blue minus state was 1 over root 2, red plus, minus, red minus.
And we had an interpretation for a difference of vectors in this case. We've simply thought of it as the state of another possible observable. Now, for the E prime state, the interpretation isn't so clear. We don't really understand E prime in the same sense that we understood what the E state means. And we don't really have a mechanism for the dice to get into the E prime state in the first place. However, the E prime state is no less reasonable than the blue minus state was, and we have all the tools we need to examine its properties.
Now, one of the most important properties of this pseudo-even state vector is the probabilities that it gives for each of the possible measurement values. And we evaluate that using our normal rule. We take the dot product of each possible measurement value with this pseudo-even state, and we square the result. And what you find is that it comes out exactly the same as the probability of each of the basis states with the even state. So for example, if we want the probability of 6, say, when it's in the even state, or the pseudo-even state, we take the 6 vector and we dot it with the pseudo-even state. These two values will give us -1, but that squares to 1, so the value is a third, which is exactly what we got when we used the even state instead of the pseudo-even state. And you can see that if we were to use any of the odd states, they would always match with a 0 in here, and so we would get 0. So we're going to get exactly the same values. So this pseudo-even state gives all the same probabilities for possible measurements as the actual even state that we initially defined. Where it differs from the actual even state is in the probability of this state actually arising in the first place. So if we want the probability of E prime, given that it's initially in the unknown state, we take our inner product of E prime with U, square the magnitude, and in terms of components, this looks like this. Now, here is where something interesting happens. We get 1 from these two coordinates. We get a second one from these two coordinates, so that's 2. But then when we get to the final coordinate, we get -1. So it's 1, 2, 1, not 3. So the probability is going to come out quite different. We're going to have 1 over root 3, 1 over root 6, and instead of a 3 in here, we now have a 1. And the probability turns out to be 1 over 18. Now remember that the probability of getting the even state from the unknown state was a half, which was the same as the classical probability of getting a 2 or a 4 or a 6. Now, we've already shown that this state produces all the same probabilities for getting 2, 4 or 6 or 0, 1, 2 as the E state does. So this can lay just as great a claim to represent the even state as our original even state can, and yet its probability is nothing like the classical probability. This unexpected probability for the E prime state isn't its only unusual property. As explained in a previous video, a quantum version of the die could actually exist in a superposition of states. It could be in the state E plus E prime. They both are just as good to represent the even state, so when we're told that it's in the even state, we don't actually know which one it's going to be in. But look what happens when we add the E and the E prime states. The 2 and the 4 components reinforce one another, but the 6 components cancel. The probability of a 6 when it's in a superposition of states like this is actually 0. This is very similar to what goes on in the double slit experiment. A source of photons or electrons causes photons or electrons to pass through a double slit, and each individual photon or electron goes through both slits effectively and ends up in a superposition of states where some positions reinforce each other and others cancel. And E' isn't the only state that can cause interference effects. Each one of the components of E can have plus or minus 1 in the 2, 4 or 6 components. That means there's 2 to the 3 or 8 possible versions of the even state, and they all produce the same versions for the possible measurements of the die. 0 if it's odd, a third if it's even. The U state itself can have plus or minus 1 in each of its components. So that means there are 2 to the power 6 or 64 possible versions of the unknown state. And each one of those will lead to different probabilities for each of the possible even states. And even this doesn't exhaust all the possible combinations. As we saw in a previous video, we can actually introduce complex numbers into our components, and each one of these can have a separate phase value. So there's not just 2 possible values for each component, there's actually an infinite number of values for each component. So the opportunities for interference are literally endless. We don't see any of these effects when we roll a die. We don't see the weird probability, we don't see the interference effects happening either. And so when we're modelling a die in terms of probability as a vector space, we would just restrict ourselves to this type of even vector and to this unknown vector. And that's the difference between this type of model and quantum mechanics. In quantum mechanics, all these weird states exist, all these weird probabilities exist, and the interference effects actually happen.